I would like to introduce you the next speaker, Mr. Fotios Galanis. Mr. Galanis is a mechanical engineer and a PhD candidate in the Laboratory of Applied Thermodynamics, thermal section of School of Mechanical Engineering, NTUA. He is experienced in techno-economic studies, SCADA design for HVAC systems, optimization techniques.
I'm currently a PhD candidate in the National Technical University of Athens, and I will be presenting you the modeling and experimental evaluation of an open cycle liquid desiccant dehumidification unit. I would like to apologize in advance because this is my first ever presentation in front of an audience. No, okay. I really apologize for that. Now, let's continue. The basic principle of the absorption process is if we start with a very strong salt solution, it will attract moisture from the air with an almost like magnetic force. In a two-part system, any concentration imbalance will cause a flow from the strong side to the weak side in order to equilibrate the solutions. And if we add the heat source to one part of the system, we create a continuous flow due to the constant imbalance of the system. Moving on, in order to do introduction to absorption refrigeration, we present an absorption chiller, which provides chilled water that can be used for cooling purposes in a building or a room, mainly in a building. The basic parts that comprise the chiller are the evaporator, the absorber, the generator, the heat source, the condenser, the solution heat exchanger, and the cooling tower, or a cooling source. It's not necessarily a cooling tower. I will not go into further details because of the time limit. Now about liquid desiccant dehumidifiers. They are mainly used in the industrial sector where eco-friendly approaches for all air conditioning are enhanced and prioritized. They have a similar working principle to absorption chillers, and they consist of the following: an absorber, a generator, a heat source, and a cooling source. Moving on, I want to mention some of the advantages of those units. That unlike conventional air conditioning systems, they provide both temperature and humidity control without overcooling the air past the condensation point, making them very energy efficient. They are also able to handle large amounts of air without the use of harmful refrigerants, thus aligning with the global effort to minimize ozone-depleting substances. They can also be integrated with renewable sources. And despite their higher initial installation cost, the investment can be recouped within 1 or 2 years of operation. Now, we must do a distinction between open and closed cycle systems. The main difference is that in a closed cycle, the air does not come in direct contact with the liquid desiccant, while an open cycle system allows for the direct interaction of ambient air with the desiccant. The closed cycle systems are used in buildings and areas where air circulation is needed because they provide better indoor quality, while open cycle systems are mainly used in the industrial sector and areas needing high capacity dehumidification, meaning they need to handle large amounts of air. And they have also a lower operational cost. Both units, unfortunately, they are characterized by the high initial installation cost and the high maintenance cost. Now, I want to present to you the unit that we have installed in the Applied Thermodynamics laboratory in NTUA, which is an open cycle cooling and dehumidifying system using lithium chloride as a liquid desiccant medium. It is also integrated with an evaporative cooler and a heating source to ensure continuous operation. Here we see the hydraulic circuit of the system, as well as the photo of the system, which shows the regenerator, the dehumidifier, and the solution tanks. Okay, moving on. The absorber. The absorber unit consists of a counterflow plate heat exchanger. The heat exchanger is constructed from 62 well-problemed seats with vertical ducts, which serve the purpose of the air and the solution flow, along with 60 black seats with horizontal ducts, which enable the simultaneous flow of water inside the heat exchanger. Now we will analyze the dehumidification process briefly. strong liquid desiccant solution flows from the strong solution tank and is sprinkled into the dehumidifier at the 2/3 of the total height of the heat exchanger. Simultaneously, ambient air flowing from the bottom to the top is inserted into the dehumidifier and it comes in direct contact with the desiccant, which absorbs its moisture. Due to this process, needs the concurrent circulation of cooling water in order to absorb the unnecessary heat coming from the dehumidification process. At the end of the process, the diluted desiccant solution is pumped to the weak solution tank, and the air cooled and dehumidified is applied back to the room. I also forgot to mention the extra cooling that the cooling water provides at the top of the unit. As far as the regenerator is concerned, it consists of 25 and 24 black and white polypropylene sheets respectively. Ambient air is blown to the bottom and flows from the bottom to the top of the unit, while the air comes in direct contact with the aqueous solution, which is pumped from the weak solution tank and sprayed at the top of the heat exchanger. If we provide the necessary amount of heat, which originates from heating water circulating in the heat exchanger, we can separate water vapor from the liquid desiccant. Thus, the solution will regain its original concentration and will be pumped to the strong solution tank. And the air, which has become moist, will be exhausted into the atmosphere. The evaporative cooler's main role is to provide the necessary amount of cooling water in order for the dehumidification process to occur. To achieve this, the evaporative cooler uses exhaust air from a room and mains water. This has a main drawback, that it limits the temperature of the cooling water to the dry bulb temperature of the room's air. But I want to mention that it requires no additional refrigerant, thus minimizing the environmental impact of the unit. As a heating source, we currently have a 24 kilowatt boiler, which provides the regenerator with heating water. The water from the boiler flows into a plate heat exchanger, which comprises the main thermal exchange bus between the boiler and the regenerator, so the two waters do not mix. The storage tanks serve the purpose to make the regeneration and the dehumidification process independent from each other, and they also serve the purpose to store the necessary energy for air conditioning in a salt solution, in a concentrated salt solution form without any energy losses. They are also equipped with overflow protection gear. Now for the data acquisition system used in the experiment. The system consists of a temperature sensor, pressure sensor, differential pressure sensors, and relative humidity sensors. We also integrate 4 data acquisition modules along with 1 data collector module. The communication between the modules and the collector will be done with a serial cable, and the collector will send the data through a serial cable and a USB converter to the control PC. All modules and sensors require an additional voltage supply, thus this is why we also install the appropriate voltage suppliers. The data acquisition modules provide 7 data channels, which are differentially configured, meaning that they can also measure current or voltage. The communication protocol used for the system comprises a custom but simple request reply protocol based on ASCII code, and it is configured according to the manuals of the data acquisition system and the system's needs overall. Here in the table we can see the tag names of the measurements, the module name and addresses, the channels, and also sensor calibration information. Here we also see the position of the sensors inside the unit. As far as the software is concerned, we have developed the data parsing method to display the data in a readable number format. We also created a control screen where also alarms will be displayed in case of a high, low, or a timeout alarm, meaning that the modules will not get measurements from the sensors. And we also programmed we also developed a different program that shows the measurements in a configurable chart format, and those data can be also exported in a spreadsheet format. Continuing to the non-adiabatic model that needs to be validated, it is based on energy and mass conservation laws and describes coherently the coupled heat and mass transfer processes taking place in the dehumidifier and the regenerator respectively. We use specific thermodynamic libraries from advanced programming languages in order to calculate the thermodynamic parameters of air and water, and we also use empirical equations from the literature in order to calculate the thermodynamic properties of the aqueous solution. Here we just have some examples about thermal capacity and thermal conductivity of the liquid desiccant solution. So before we proceed with the equations, we need to make some assumptions concerning the basic geometric characteristics of the absorber, and some additional assumptions for model simplification and model of convergence. I will not go into further details because of the time limit again. The following set of differential equations represent the change in the air's temperature, the solution temperature, the air's absolute humidity, the mass flow rate of the desiccant solution, and its concentration. The system can be also solved as a boundary equation problem using the appropriate library with the following boundary equations. In those tables, we present the data from one of many experiments we conducted. We measure air temperature, solution temperature, water temperature, air absolute humidity, and solution concentration. We observe some deviations that we'll discuss. We also present the data in figure format. The right figure shows the change in absolute humidity of the air as a function of its temperature. And the left is an equilibrium diagram of the solution, which also shows the change in the solution temperature as a function of its concentration. The conclusions from the comparison are that the model underestimates the cooling capacity of the dehumidifier as it does not consider the further cooling of the air exiting the unit through the air-water heat exchanger installed at the top of the absorber. There seems also to be a difference between the liquid desiccant temperature of the model and the experiment, which might indicate some wrong calibration of the sensors. The difference between the simulated and experimental measurements of cooling water and exit temperature is occurring due to underestimation of the total heat exchange coefficient, which originates from false assumptions about the plate thermal conductivity, mainly from the plate thermal conductivity, and kind of the water's heat transfer coefficient. Inaccuracies concerning the solution concentration for both the absorber and the regenerator occur due to the lack of a constant solution mass flow meter in the current data acquisition system. To sum up, it is of vital importance to obtain data from those units because they have a very low environmental impact. The goal of this work was to validate the existing theoretical model through experimental measurements obtained by a data acquisition system for a liquid desiccant humidifier and the regenerator as well. This can be used for future energy and exergy analysis. The data acquisition process encompasses sensor position, calibration of the sensors, and the creation of a control screen, where the validation process involved implementing the model using an advanced programming language due to its plethora of libraries for thermodynamic analysis and comparing the experimental data with theoretical results. I want to say that further developments need to be done in those units because of their very low environmental impact. We need to develop more advanced simulation models for those units, integrating model predictive algorithms and advanced control, humidity control, and temperature control. This needs to be done in order to promote some resilience in the face of the global climate change and promote, in general, a greener future. Thank you for your attention.
Before the questions of the audience, I would like to ask you something. By having these experiments, did you notice that you have outcomes that you can use with regeneration temperatures lower than 55 degrees?
The main, I don't think that we can work with lower than 55 degrees. Maybe 50, but not lower than 50, I believe.
Thank you.
So far. So that's why further research needs to be done, using this data acquisition system, improving this data acquisition system, etc.
Thank you very much. Any other questions?
Great presentation, and your last slide at moving toward a greener process. Just give us an idea of what you think the first step to decarbonizing that process might be.
The first step is to integrate that unit with a solar heater, with renewable sources. This is the most important part. Then we need to investigate how its performance will be. We'll integrate it with that solar heater. So we need to use artificial intelligence, optimization methods, and the list goes on.
Yeah, you could also use waste heat from other processes in the building.
Of course, but I don't think that's possible in a lab.
Not
That's the reason I asked you about the 55 degrees, because the thermal solar heaters are losing their efficiency with temperatures higher than 68 degrees. So the combination will be tough.
Okay.
Thank you.